Advanced Router Technology Part 7, Multicast Routing Concepts. In this conceptual nugget, and I want to emphasize that, we're going to talk about the concepts of multicast routing, really laying the foundation for what multicast is all about. I'd like to start off this nugget by getting into the facts of multicast routing, bringing everybody up to the same speed and on the same page with what multicast is all about and how some of the communication and addressing works with multicast. We'll then move into the multicast source trees versus shared trees, two different logics of how multicast can be deployed. It's really kind of design standards of how you will design your network to support multicast. Then we'll get to the actual protocol that's used to deploy the source tree and the shared tree, and that will be PIM, Protocol Independent Multicasting. PIM is the routing protocol, if you will, of multicast. This will allow you to figure out how to get around your network and what streams to allow through your network for the multicast routing. There's two modes that we're going to discuss. It's going to be PIM dense mode, which is beautiful in the sense that it's easy to configure, and then sparse mode, which is beautiful in the sense that it is very efficient. Two different competing modes that you can actually combine together some of the functionality to get the best of both breeds in your multicast network. The term multicast has been used to describe many different technologies over the years, and when most people hear multicast, they think, oh, well, that's audio streaming or video streaming, sending out some sort of streaming technology. And that's by far the most popular use of multicast, but the official definition of multicast is that it's a technology allowing a host to send a single stream of traffic to reach any number of destination hosts. Now, before multicast had come about, the only two ways to reach a group of hosts was to send out multiple unicast messages or to send out broadcast messages. So first off, if this IP video server was sending streams to 3 receivers using unicast, and those streams were maybe 1.5 meg each, which is about the bandwidth you need to do a full screen video DVD quality style transmission, that would mean that it would have to send out 1.5 megabits per second 3 times. So by the time it's said and done, you have about 4.5 megabits per second being used. And if this is a 10 meg link, you probably peak out somewhere around 6 or 7 sessions before you run out of bandwidth. Furthermore, every single link on the routers and the switches eventually that reach these receivers are also going to be saturated with more bandwidth. So instead of having single streams unicast out, the alternative would be broadcast, which in this environment wouldn't work because that's what routers are there to stop. A broadcast is one message going to everybody, and that has its inherent disadvantages as well. So multicast allows this one IP video server to send one message, and what will happen with that one message is it will be sent out to only a group of receivers, specific receivers that have purposely tuned in to that multicast frequency. And as we get more into the different terminology of multicast, that's really what multicasting is tuning in to a specific radio station of a multicast frequency. But instead of calling them radio station frequencies, we call them Class D addresses. This is going beyond the standard IP addresses that we use for addressing our hosts into the range of 224 through 239 as the first octet of the IP address. Now, when you subscribe to one of those IP addresses, and that's really one of the terms that you have to get used to, you are denoting yourself as a member of a recipient group rather than an individual host. And here's the concept. You might have a server that's sending out streaming audio. Maybe it's a radio station server, and it's sending out streaming audio to 239.1.1.1. That is going out, and it's reaching all these different routers all over the place. Now, you as a host somewhere down the line will eventually say, you know what, I'm going to tune my multicast radio frequency tuner to tune in to the address of 239.1.1.1. Now, that does not mean you replace your source IP address, that you suddenly respond to a different IP address or have some other alternate method of communication, but instead, your network card is now tuned to this frequency, and that will notify this router to tune in. And we're going to get into how the routers kind of communicate to each other what frequencies or multicast addresses need to be sent across what different wide area network and local area network connections. But looking more at the facts right now, the multicast range 224.0.0.1 through 224.0.0.255 is all reserved for network protocol use and has a time to live of 1. Now think hard back to the routing protocols and what we covered in those nuggets. We saw OSPF and EIGRP, even RIP version 2, use multicast for communication. So what you would have is you have a group of routers that tune in to a specific multicast address and they will respond to any messages sent to those multicast addresses. Now this little fact hops in here, time to live of 1. What that means is when somebody sends a message out to one of these multicast addresses, the routers will receive it, but if a packet has a time to live of 1, will it ever be propagated through a router to some other attached network, maybe another router down here? No. Time to live is decremented every single time a message goes through the router. So if it has a time to live of 1, it will only reach a directly connected neighbor that's on the same network segment and then not go any further. That router, if it needs to, will originate its own multicast message for that segment. So every address starting with 224.0.0. something is going to have a time to live of 1 and most of the time be used for a specific routing protocol or some sort of network protocol using it to communicate. Now what we'll see most of the time in our examples is the multicast range of 239.0.0.0. It's an entire kind of class A style range, a subnet mask of /8. Those are equivalent to private multicast addresses. If you want to use multicast within your organization and not have it leave to go beyond the boundaries of your autonomous system, that is the address range that you want to use. Maybe you have a private video broadcast from your CEO covering all of the financials of the company, but it's only meant for internal users. In that case, 239 would be the multicast address range that you want to use. You can also start getting into the multicast standard, and I'm not going to go that far, but there are other reserved ranges, and you can even go so far as to get into BGP. BGP, each autonomous system that is considered a public autonomous system has its own multicast address. It's a brilliant method that they've used to convert your autonomous system number into a multicast address that your organization can use to send messages across the entire internet. Now, how's that possible? Well, the internet still has a quasi-experimental system called the M-bone, the multicast backbone of the internet. And while some people are now starting to use it in a production sense, it was really deployed as an experiment and is still considered experimental. Now let's focus on what we're here for, the routers. How do they determine what sort of multicast traffic to forward and what multicast traffic to not forward? Because think about it, if we had the internet and every time some server started sending a multicast, if all the different routers on the internet started forwarding that multicast, we would have a crisis. We would have all the bandwidth used up on the internet by these constant multicast messages. It would be essentially just like forwarding a broadcast across the internet continuously from multiple sources. So that can't happen. The first way that we can use to tune and design a distribution method for multicast is a system of what's known as source trees. A source tree is typically used for a smaller organization, and I'm going to apply this to a Cisco spin in just a moment when we talk about PIM. But a source tree design method means that all of your routers in your organization will track the multicast servers based on their source IP address and their group number. Here's what I mean. I'm going to go ahead and jot it up right here on the screen. Let me put it in black so it's easier to see. It will look at the source IP address that is sourcing the messages and the multicast group. So in this case, we have a server that is 192.168.2.1, multicast group 239.1.1. Every router will instantly create an entry in their multicast routing table, which is totally separate from the IP routing table, and it'll look something like this. 192.168.2.1, comma, 239.1.1.1. So we have the source IP and the multicast group that is used to figure out what that stream is. So what happens is all these routers will create an entry in their database that looks something exactly like that. Now, does that mean they're forwarding traffic for that server? No, the answer is absolutely not. They're not forwarding anything until a client requests it. They just know about this stream that this server is constantly broadcasting out, or I should say multicasting, streaming out. Let's say, for the case of this example, that it is a constant audio stream. You create music for your organization, some of that music that's kind of calming. So if any computer wants to tune into that, they can get music at any time of the day. So at this point, anytime, you might have some specific application on this host, and it says, I want audio. So I'll put a little happy face here to let you know this guy wants the audio. Well, that will be sent to the default gateway as a request for the multicast stream, and the application will be requesting 239.1.1.1. This router, which knows about that stream, will kind of start opening floodgates. It will say, okay, well, I need to activate a link. I need to send a request for the multicast stream to be sent so that I can tune into it. That comes back up here to router A, and router A will now kind of open up the floodgate, if you will, to allow that multicast message to flow down. Now, this client will tune into that and be grooving to their music tunes until that application is closed. As soon as it's closed, this will prune off and cut that stream and essentially close that floodgate again to keep the stream, the audio stream, from going across. But the key is that all the routers will always know that this stream exists. It's kind of like a multicast routing table. They always know what streams are currently active all over the network. Now, that is fine for a small organization. That's the idea of a source tree. But when you start growing your organization larger and larger, and maybe even scaling it to something the size of the internet, you're going to have potentially hundreds, thousands, tens of thousands, maybe even millions, if you're talking the internet, of multicast addresses that will always be sending out audio or video streams. That will cause your multicast routing table to get larger and larger. So for those organizations or networks of that size, we might move from a source tree to a shared tree. With the shared tree multicast design, you will designate one or more master of the multicast routers. And what those are officially called is a rendezvous point. Now, what happens is all of the multicast sources will come and register with the rendezvous points. Now, the rendezvous points are the ones that have the full database. They know where the multicast messages are coming from, what source IPs, what multicast groups are supported. They are the kings of the multicast network. So what's that leave all the other routers as? Well, they essentially at that point become multicast clients in a way. Here's what I mean. Before, when we saw the source trees and we started looking at how it's tracked using a source tree, we saw that it was done. All the routers keep a database of the source IP followed by the multicast group. Well, the rendezvous point will still track that, but now you'll actually have the rest of the routers having something like this comma, and then their rendezvous point IP. You can almost think of them as having a default gateway in a multicast sense to the rendezvous point. Now, do make sure that you understand that this is talking about multicast. I'm not talking about the routing table. OSPF, RIP, static routes, that whole story, that's a separate ballgame. Multicast creates its own little world, its own little routing table that it's going to use. And when you use a shared tree method, all of these routers are going to point to the rendezvous point as their source for multicast. So here's the rest of the story. When we have a client that wants to subscribe to a stream, let's say that this client over here now tunes into that audio stream that's coming from this server, it's going to send a request to E. Now E is going to say, well, I don't know if that group exists, but I do know that the rendezvous point will be able to tell me. So E will ask the rendezvous point and say, excuse me, do you have this multicast stream? The rendezvous point will say, well, absolutely yes. I have that multicast stream and I can tune you into it. So the rendezvous point essentially acts as a proxy at that point. It will tune in to that source stream, tell A to open up the floodgates to start sending it out, and it will be the one that sources the multicast coming down here to this client attached to router E, so this guy's starting to hear the music tunes coming through their speakers. Now, you might look at that topology and say, well, wait a second, does that mean that we can have some inefficient routing if we use a shared tree structure? I mean, let's say that instead of B being the rendezvous point, C was the rendezvous point, and this router E tried to tune into the stream. Does that mean the multicast stream has to come over here through C, then back through B, down to, and then hit E? I mean, do you see the problem that I'm painting here? The answer is no, because shared trees also integrate a lot of the source tree technology. Here's the idea. The routers still act as dumb terminals, essentially, in the fact that they don't know where the multicast groups are or how to get to the sources. But when they open that stream, and when router E says, I need to request, I need to see if that's available, it will not only see that it can be provided from the rendezvous point, which is a good strategy, but it will also see what the original source IP and the group is. And this is one of the few times that the routing table and multicast really start merging together. Router E will look at its routing table and it will say, okay, I can choose to get this stream from router B, or I can go with a source tree structure. It can kind of flip back into the source tree mode, and I can go to the server myself. So let's say maybe going through D happened to be a little more efficient than going through the rendezvous point because these links had less bandwidth or whatever the case may be. Router E can convert back to a source model once it figures out what that true source IP address is, and it can go up to the source IP address itself and get the multicast stream directly. So shared trees are, all these S's begin to merge together. Shared trees are much more efficient than source trees. Some might be wondering, well, why would I ever use a source tree over a shared tree in that case? Well, because source trees, and when we start getting into the PIM technology, you'll see that source trees are much easier to set up. It's almost like just flipping a switch and turning on a source tree. There's not much configuration that needs to take place. To configure a shared tree will take some work and also some good design on your part. You can see that that rendezvous point or points should be the routers that are residing somewhere around the middle of your network. They should be the big guys, the ones with all the power and all the connectivity of your network. So it's time to pull the curtain back and pull out the engine behind this all. That is going to be PIM, standing for Protocol Independent Multicasting. Now, what is PIM? Well, PIM is the routing protocol of your multicast network, and that is the most accurate description that you can really give it. Just like you have OSPF and RIP and static routes that build your routing table for unicast messages, well, PIM will build your routing table for multicast and allow multicast communication to happen through your router. Now, the reason it's a little odd is because PIM, at times, can look to the unicast routing table to find its best way around the network. When you talk about something like PIM, you're not going to get into the sophistication of OSPF. There's no areas or autonomous system boundary routers or any advanced mega configuration like that or redistribution. PIM is just a simple protocol that communicates the multicast groups around this network so that all these clients will be able to tune in. So a lot of times you may find this relying on your unicast routing table to find its way around the unicast-based network. So let's talk about the first mode called dense mode. This is the way that you can implement a protocol, a PIM version of a source tree. Now remember, the source tree was the one that was very simple to configure, where all the routers know about everything that's happening every point in time. This is the best way to configure a small network. And here's the concept of PIM dense mode. You're going to go to each router, and for whatever interfaces you want to participate in multicasting and sending multicast messages, you will go under the interface configuration and enable them for PIM dense mode in this case. And we'll talk about the other modes in just a moment. Let me show you the one command that you are going to use. Let's say that this interface right here is serial 0/0. You would go under the interface configuration mode for that serial interface, and you would type in IP PIM followed by dense mode. That's it. That's the only command that will enable your whole routed network to now support multicast routing and support multicast messages. You're going to go under each and every interface. We'll say serial 0, serial 1, serial 2, every interface that will be connected to the multicast network, and type that one command, IP PIM dense mode. Now, it's very easy to configure. One command does it, but here's the disadvantage. If we go with that easy configuration, what will happen is initially this source multicast server, let's say it's sourcing some music, will start sending the music stream. Router A, because it's using PIM dense mode, will start sending that multicast stream to all of its friends. All of the interfaces that are enabled for PIM dense mode will start getting that stream going across, and it will fly across the whole network. That's right. Every router that's enabled for PIM dense mode will get that multicast message and pass it on to all its attached interfaces that are enabled for that. So you can see right off the bat, yikes, that is not something we would use on a network the size of the internet or even large enough for most organizations, because having that stream go across is a pretty brutal hit to your traffic, especially if it's a pretty decent sized stream. What will happen is all of the routers will get the stream, and then they will begin to slowly prune back. For example, router C might say, you know what, I'm not getting any clients on this network requesting that stream. So you know what, I don't need to receive that stream. And router B will say, you know what, I'm not getting any requests either. So you see what's going to happen is they will all begin to start pruning that network back one branch at a time until finally, if nobody's requesting the stream, it's gone back to router A, and it's just kind of containing that stream inside until one of the clients requests it. Now, the other disadvantage of PIM dense mode is the protocol resets itself once every 3 minutes. Wow, what does that mean? That means once every 3 minutes, the whole story begins again. All of the routers will begin forwarding that multicast message to all of the other routers, and they will all start pruning back, cutting it off one more time, preparing again. Once every 3 minutes, it's going to happen again. You ever have somebody tell you the same story again and again and again? That's the same thing here. It's always going to be the same streams again and again and again coming through, and all the routers will get it and have to cut them back. So PIM dense mode is ideal if you have, per se, a network that looks like this. 5 routers, no more. Small networks will usually use something like PIM dense mode just because of its ease to deploy. I've come to think of PIM dense mode the same way I think of the RIP routing protocol. When I first saw it, I thought, wow, who would use this routing protocol when things like OSPF and EIGRP exist? Well, the truth is a lot of people use RIP because it's quick and it's easy to deploy and it works for small networks. PIM sparse mode, on the other hand, is the OSPF, if you will, of the multicast routing protocols. Sparse mode is the implementation that allows you to use a rendezvous point and set up a rendezvous point on the network that all the routers point to. So let's say that we have a client hanging off of router A that wants to tune into that stream. What's going to happen is this is always sending the stream and router A is always receiving it. But this sparse mode will implement what is known as a pull mode. The dense mode is known as a push, where it's trying to push the multicast stream on you. The sparse mode is a pull mode, meaning that the routers are only going to pull that source if they need it, if it's had a request. So if this client goes ahead and requests the multicast stream, it's going to go to router A. Now here's the catch with sparse mode. Router A is configured with that kind of default gateways, the star, the asterisk, everything goes to the rendezvous point first. So it's going to ask router B, and it's going to say, do you have this multicast stream? And router B will say, why, yes, I do, and it's right through you. So for an instant, there may be a moment where router A opens its little floodgate of multicast traffic, and it's going to flow to router B, and router B is going to forward it right back to A. But that'll only happen for a moment until router A gets that source and has the chance to figure out, well, wait a sec. That source IP of 192.168.2.1, sourcing the multicast group 239.1.1.1, well, they're right next to me. So what's going to happen is it will very quickly figure out, you know what, I don't need to go that way. I can just source it directly through here. And that allows the sparse mode to become a very efficient protocol to use, because not only does it implement the pull technology, meaning you're not going to be flooding your network needlessly like dense mode does, but it also implements the efficiency of the dense mode in the sense that these routers will figure out the best way to get to a multicast source, even though initially they all have to go through that rendezvous point. In this brief nugget, we've had the opportunity to go through the 3 concept umbrellas that I wanted to make sure we were all on the same page on before we get into the multicast configuration. We started off with multicast routing, the facts, kind of the facts that you need to know about multicast before you can really get into the configuration or the concepts of how to design a multicast network. We then looked at multicast source trees versus the shared trees. Really the design aspect of multicast, 2 different ways that you can set up your multicast network to communicate. And the nice thing is as we got into the actual implementation of these things, these concepts with PIM, PIM allows you to combine some of the concepts of source trees along with some of the concepts of shared trees and implement them in what's known as PIM sparse mode. PIM dense mode is the quick and dirty way to deploy multicast routing to get it up and running on your network, but for true efficiency, you want to use PIM sparse mode. In the next nugget, we are going to take a look at the actual implementation of PIM and set it up in many different scenarios on our multicast routers. I hope this nugget has been informative for you, and I'd like to thank you for viewing.